for the introduction and the great honor of speaking at this seminar, um, and gives me an opportunity to talk about my recent work. So, um, the origin of the story is from David Hilbert, and one of my pet peeves is that depictions of Hilbert for his 1900 ICM address is always of him as an old man, but I looked at his age, he was only 38 at the time. And they tend to use pictures closer to the end of his life, maybe in his 60s, to refer to his time. So at least I, as a student, got the impression that Hilbert was quite old in 1900, but he actually wasn't. He's the same age as I am right now. So, but in any case, he asked 23 questions that he thought would be very influential in the 20th century. And his 10th problem is no, well, is the assertion that there should be an algorithm to decide for an arbitrary polynomial or a system of polynomial equations. There should be an algorithm to decide whether or not that system has an integer solution. And that was actually how Hilbert phrased it. So he thought that such an algorithm must exist. But of course, we know that he was wrong in the sense that such an algorithm cannot exist. And this is a culmination of several decades worth of work and culminating in Matiyasevich's work, which closed off the problem. Um, so, whoops. Inspired by their work, Buchi, who was, we would call him a computer scientist today, but that job didn't exist in his time. So he investigated, okay, well, can you loosen the requirement, instead of having an arbitrary system of polynomial equations, you bound it in some way and see if you could recover decidability. And he thought about bounding the degree. So if you have the lowest possible bound, which is 2, every equation has degree 2, and you can even make the equations as simple as possible, conditioned that their degree is 2, which means that you have just diagonal quadratic forms as your equations. And he uh, realized that even in this case, you are probably not going to get decidability. And the reason why there's a caveat of probably is because his proof relied on a hypothesis. So, what was this hypothesis? Is that if the squares of integers behave in a certain way, then this algorithm can't exist. So the hypothesis was that there exists some positive integer n naught, such that whenever n is at least n naught, any increasing sequence of squares with constant second difference equal to 2. So this is something that consecutive squares, this is a property of consecutive squares, right? If you take any string of consecutive squares, their second difference will be 2. So this is saying that if your string is long enough, then that's all you get. You cannot have a non-consecutive sequence of squares or increasing squares where the constant second is 2 um, if n is big enough. So soon after this problem was proposed, Doug Hensley provided in an unpublished work an infinite family of non-trivial quadruples of squares with constant second difference equal to 2. So he actually gave a polynomial family. So Xavier Vidot, who, as far as I know, is one of the people who worked quite a bit on Buchi's problem over the years. So he found a lot of other infinite families. So there's probably a countable family of polynomials or polynomial families that give you solutions. So another key result was due to Vojta in the 90s. So he took the perspective that Buchi's problem can be interpreted in terms of algebraic geometry. So if you assume that, say, Buchi n-tuples exist, then they correspond to some surface in, I think, Pn minus 2. And but the dimension of the variety itself doesn't change. It's always a surface. It's just the ambient dimension changes. So he realized that if n is large enough, then the surfaces become general type. So you can apply Bomberi-Lang. And of course, Bomberi-Lang doesn't tell you that there are no solutions. It just says the solutions are not Zariski dense. So the input of Wojta is that aside from the obvious subvarieties, and they're actually just lines containing basically all the trivial solutions, there are no other interesting curves, and in fact, there are no sporadic solutions neither. So essentially, he proved Buchi's assertion with n naught equals 8, assuming Bomberi-Lang. But you really need Bomberi-Lang to rule out other weird curves that you can't directly prove that they don't exist. So actually, Buchi suggested, without the benefit of seeing these constructions, that somehow you should be able to take n naught equals 5. Okay, and this is what we proved today. So this is sharper than Wojta's result because he can only do it for n naught being 8, and this is claiming this result for n naught equals 5. So I'll try to give a sketch of the proof, and I've given a talk on this before, but I can never get to the last part or where the interesting things happen for the proof. So I'll try to push us towards getting a glimpse of what happens because I think it's pretty glorious. Okay, so strictly speaking, we are reducing Buchi's original problem to something slightly different, and our techniques should allow us to play around with the structure, and a specific set of parameters corresponds to Buchi's problem. But if you choose other parameters, the techniques should still work, but it's not clear what you would get out of that, like what problem would it solve or correspond to. So another remark is that we use integrality a lot. So Wojta's proof, which interprets things as projective surfaces, right? There's no difference between rational and integral points. But for us, the actual integrality plays a crucial role. So you can interpret this as the difference between integral and rational points on surfaces. Okay, so the starting observation is that if you forget about squares, right, the requirement that the second difference is constant equal to 2 is just a linear recurrence condition, right? So you're just trying to solve this linear recurrence, and well, I don't know exactly when you learned this, but pretty early, I think. A lot of high school students can do this. So you can solve this explicitly as some closed form, where alpha and beta depend on the initial conditions. So you can now interpret Buchi's problem as follows, right? This is just a quadratic polynomial. And it turns out that in order to have a non-trivial tuple, you must have the discriminant being non-zero. So does there exist a monic quadratic polynomial with non-zero discriminant, which represents squares at 5 or more consecutive integer inputs? That will correspond to a non-trivial Buchi tuple. So we can actually figure out what the initial conditions are if we just have initial string of squares. So just again, this is pretty simple. Just a little bit of algebra. You can express alpha and beta in terms of the first two terms of the sequence, which are both squares. So if you actually have a sequence of squares where the constant second difference is 2, then consecutive terms must have opposite parity. So if alpha is, so because of this condition, this form of alpha tells you that alpha has to be even. Okay, so we can write alpha equals 2 times gamma for some integer gamma. So this reduced discriminant is always a multiple of 4. So this turns out to be important. So this is just a simple case analysis by looking at congruence, because either x naught is odd and x1 is even, or x naught is even and x1 is odd. And in both cases, you conclude that this reduced discriminant has to be divisible by 4. So we also have positivity. Again, it's just opening up what gamma and beta are. And if you do it, you realize that, okay, so it factors very nicely. And this term is always going to be positive, right? Because we assume that x1 and x naught squared are a sequence of increasing squares. But this term, well, it could be zero, but then you have consecutive squares. So any non-trivial sequence would correspond to positive discriminant, as claimed. So because the middle term, right, because as we recall, alpha must be even, which means that it plays nicely with translate integer translations for quadratic polynomials. We can shift the polynomial into this form, x squared minus 4d, because, like I said, the discriminant, or this d must be divisible by 4. So in this shape, right, we can ask for such a polynomial, can we find one where with d non-zero, or actually positive, that represents squares at 5 or more consecutive inputs? So assuming that we can write the left-hand side as a square and the right-hand side as some input. And then the sequence is defined with this property that because the inputs have to be consecutive, right? So that's what we end up with. So I think this is called squares and quadratic progressions. So there is a mathematics, a computation paper that looks at these things. So they consider this problem, but in more generality. So they consider not necessarily monic progressions, but just arbitrary quadratic polynomials. And they found, you know, fairly long ones. Okay, so we exploit the fact that if we move the sk to the left-hand side, we have a difference of squares, which we know how to factor. So we can write this as sk minus tk times sk plus tk equals 4d. And we make a change of variables. We write xk equals this and yk equals this, and we end up with the condition that the product is 4d. And if I add up xk and yk and I subtract, then I just recover this difference condition. Well, if we look at this, these two terms, which are xk and yk, always have the same parity, but their product is even, so they must both be even. So we could just divide through by 2, and by abuse of notation, change the condition to this, which is cleaner. So really, it's not about the original squares anymore. It's about these pairs. Okay, so that compels us to make a definition. So we're going to define an M2-pole of Buchi pairs to be a two-pole of pairs of non-negative integers xi, yi, with the pair satisfying the above condition. And one thing that I'm going to comment on right now is that at some point you're going to swap the roles of xk and yk. So it's not literally, you're not locked into this definition. It's just you stay with this, but when you um, reduce it, right, at this stage, xk and yk are symmetric. Okay, and that symmetry is actually going to be useful for the proof. Okay, so the above condition, which is this, that the product is D, and if I add up the consecutive terms and subtract the sum from the previous index, I get 1. Okay, so the hypothesis that the product is constant for every term, for every index, means that we can write what I call transfer variables, right? So for any pair of indices, you can compare them like this, where, well, xi is going to contribute a part to xj, and then the rest of it has to go to yj. And same thing for yi, and that's symmetric as well. So the indexing indicates, so the v's are what the xi's transfers to xj, so it's symmetric. Vij and vji are going to be equal. Same thing with the wij. But the u's has a directionality because you're going from x to y or y to x. Okay, so uij and uji are not equal, okay, in general. So we call these terms transfer variables. And what use are these transfer variables? And this is actually one of the key components of the proof and why integrality matters so much for us. So the utility to define these transfer variables is that you have this identity, right? If we look at this condition and just telescope, we're going to get this in general, right? If any index j greater than I, you have this difference. And if you substitute the transfer variables for xj, yj, xi, yi, as in the previous slide, you can group them together, and this turns out to be a product. Well, for example, so this is really restrictive because like J minus I is not huge, right? Because we're trying to show that, say, for example, 5 tuples don't exist. That means that J minus I is like at most 4. And especially when J and I are just consecutive, then the left-hand side is just 1, which means that both of these things have to be 1, basically, or plus minus 1. And like I said, you can swap the roles of xj, yj for every index. You can also assume a sign condition. You can assume both of these are positive, which means that they're just exactly equal to 1. Okay, so you see that it's really crucial that we're dealing with the original Buchi problem where the consecutive differences are 1, and we're exploiting the fact that there's not a lot of ways to factor 1. Okay, so this factorization is just this slide just to emphasize this was really important that we can factor things this way, and this product form is really helpful for the transfer variables. Okay, and also that integrality is crucial. Okay, so this is something that I did my best in writing, but I believe there must be some subject in mathematics, which is not number theory, that have a better name or a better setup for what I'm doing here. So it turns out that figuring out how to label the variables properly is really important. So generalizing the notion of transfer variables, we're going to define something called parameterizing sequences. Okay, so first you start with the bijection from f2 to the n, which is just binary, to the set of integers from 0 up to 2 to the n minus 1. And what you're going to do is you're going to take a binary string and just assign it to the corresponding integer. You're just going to write this in binary, basically. Okay, so that means that the generic element in here is going to be just written in binary, and then that's the inversion, or that's the inverse map. Okay, so we're going to define these Snj epsilon, and epsilon is just a bit in 0 or 1, to be the subsets of these integers consisting of those elements whose jth bit is equal to epsilon. So everything else could be whatever it wants, but the jth bit is locked in at whatever epsilon is. And then we're going to define a projection, basically a projection function from this Snj epsilon, and we're just going to take a vector in here and take the product. Okay, but only for the indices that are in here. Okay. So then the parameterizing sequence of n-tuple Buchi pairs is, well, if you have an n-tuple of Buchi pairs, then the 0 bits are going to correspond to xj, and the 1 bits are going to correspond to yj. Okay, so this is how you label them. And you might ask, okay, this looks like a really weird way to label things. And I'll just say this, I label things in a bad way, and it made things a lot harder because you can kind of flub it for 4 tuples, but when you try to deal with 5 tuples, which means you have 32 variables, and you don't have a reasonable accounting system for that, things can get out of hand really, really fast. Okay, so we say that the parameterizing sequence S is non-trivial if the corresponding n-tuple Buchi pairs is non-trivial, which in particular means that none of the elements in this vector can be 0, right? Just because of the definition that this is some sort of product. Okay, so if one term is 0, then it's going to force the corresponding xj or yj to be 0, and you're going to have a trivial Buchi sequence. So the proof is basically boiled down to showing that these positive parameterized sequences cannot exist for n equals 5. So this requires to show, so first is that, well, if I actually have a non-trivial n-tuple Buchi pairs, do I even have a positive parameter sequence to begin with? Maybe none of them are 0, but there could be negative ones. Okay. So it turns out that just a simple induction argument shows that you can always have a positive parameterizing sequence, assuming you start off with a non-trivial n-tuple Buchi pairs. So for n equals 2, um, the transfer variables behave more intuitively because they're just a GCD. Again, GCDs are positive. So you can show that the transfer variables are just given by the GCD of the corresponding terms. And that's just because there's no way to factor 1. 1 doesn't have any prime divisors. That's why you have this equality. So I'm just kind of blast through the proof here. So this is just a case analysis that basically if you have any common factor, you're going to violate this condition that the sum or the difference of consecutive sums is equal to 1. Okay, so 1 doesn't have any non-trivial prime divisor. Okay, so now we know that they exist for n equals 2. We can just start building them up. So the idea is, well, by induction hypothesis, you can assume, well, sorry, if you start off with an n-tuple of Buchi pairs, non-trivial, then if you subtract or remove the last row, you're going to get a n minus 1 tuple. And by induction hypothesis, that has a positive parameterizing sequence. Okay, so let's say R. And what you're going to do is you're going to define S from R as follows. For each Rj, you're going to let Sj be the positive divisor of Rj transferred to Xn, right? Because this requires you to know what Xn already is because you're given the n-tuple, right? This does not allow you to construct an n-tuple from an n minus 1 tuple. Okay, so that's very crucial because otherwise, it will contradict what I'm trying to do. Okay, but you already know what xn is, so Rj is going to transfer something to xn. So let that whatever that is be Sj, and this is what it's going to be transferred to Yn. And you see that this is respecting like the bit condition, right? So this is essentially saying that the bit corresponding to the last position is 0, and this is saying that the bit corresponding to the last position is 1. So because we already know it's an n-tuple Buchi pairs, we have this equality. So that means that these are always going to be complementary divisors of Rj. So as constructed, S must be positive, okay? And we just have to show that S is a parameterizing sequence. So this is just playing around with the definitions, right? So Xj, this is just from the definition of a parameterizing sequence. So our construction shows that how we can split how we can split Sk in both cases. And well, you rearrange things, and again, just by definition, by sorting the bits, well, you get that this equality gets recovered. And that just tells you, by definition, this is a parameterizing sequence. Okay, so there's really not much happening here. It's really just bookkeeping and maybe justifying that this way of labeling things is beneficial. Okay, so yeah, so this is just showing that yes, so this is the actual page that has the calculation, which shows that xn and yn are, or for the very last index, that the parameterizing sequence condition is also satisfied. And that means it's a parameterizing sequence for the entire n tuple. Okay, so now let's start with triples. So now I can talk about the overarching strategy of how to show that quintuples don't exist. Well, triples definitely exist, and there's an abundancy of them. But as far as I know, prior to this work, no one tried to figure out what all the triples are, right? So to classify all the triples, there are even infinite families of quadruples, so certainly you can do that for triples, but nobody said, okay, all of them must look like this. So that's where we start, and that's kind of why the rest of the proof works, is because we have such strong control. Like we know exactly what the triples look like, and that amount of structure can be leveraged to squeeze out, the room for existence for longer tuples. So by using the parameterizing sequence way of labeling, this is what it is. Okay, so um, Maybe for now you don't really care about exactly how it's labeled, but for example, x1 is just all the even indices, and y1 is just all the odd indices, and that's going to be the same for any length of tuple. The first term is just all even and all odd, corresponding to the first position being 0 or 1. Okay, so we write out all the transfer variables in terms of the SIs. Okay, and we have all of these equalities. So if we look at U3, the last one, 1 and 3, then we don't have, uh, we just get this equals to 2. But we only assume that these are positive. So we don't know which one's 1 and which one's 2, right? Because either this is 1 or this is 1, and the other one must be 2. Unique factorization, but we don't know which one it is. And there's no obvious way to use symmetry or something basic like that to insist on which one is which. So we just have to accept both possibilities. Okay, so well, we are just going to say that this one is beta, and beta is either 0 or, sorry, 1 or 2. And well, the Buchi triple, in terms of the parameterizing sequence, the parameterizing sequence has to satisfy the system of equations, where we're taking beta to be this. Okay, so this is very clean. So that, of course, allows you to remove 4 of the terms, right? Because you have 4 linear equations. Okay, so using this, we leverage that into building a quadruple. Well, a quadruple is just 2 triples slapped on top of each other, and each triple has some equation, has to satisfy some equation like this. And that seems fairly restrictive. Okay, so you see how proper labeling is going to be relevant, and this already looks kind of unwieldy. All right, this is 16 variables for quadruples. Okay, so this is for a quadruple of Buchi pairs, and this is using all the raw terms from the parameterizing sequence. So like I said, if you can obtain 2 triples from a quadruple by deleting the first or the last row, and you can use proposition 5, which is this one, allows you to which gives you equations for them. And using proposition 5 to both of them, you recover similar equations, 2 systems. Okay, and of course, beta 1 and beta 2 don't have to be the same, right? Because in each case, there's no control over the exact value of beta 1 or beta 2. Okay, but you look at this giant system and you stare at it. Well, you can actually rearrange it so that the indeterminants are S3, S6, S9, S12, and the coefficient matrix is this. Okay, and when I say a linear equation, the right-hand side is just a 0 vector. So, okay, if you look at this, this is a skew symmetric matrix. And I don't want any of this to be 0, right? Because they're terms in my parameterizing sequence. So in order for this to be a non-zero vector, that means my square matrix has to be singular. But the problem is that it's skew symmetric. If it's singular, then the rank is at most 2. Okay, so you get a bonus reduction in the rank just by insisting it's not full. Okay, so this slide just continuing what I said, right? You want all 4 of these terms to be non-zero, and so you want this matrix to be singular, which means that its Pfaffian has to vanish. Okay, so the Pfaffian, uh, I clearly did not just compute it in my head. In fact, I didn't compute it at all. I used a computer, right? But a computer tells me the Pfaffian is this. Okay, or I use Sage to be more precise. So these Pfaffian equations turns out to be what you need to scuttle the existence of quintuples. Okay, so this is the first of several types of Pfaffian equations we'll counter. Okay, so these are the reason why quintuples cannot exist, but quadruples can, because quadruples only has to satisfy one Pfaffian equation, and that's doable. Okay, so from here, again, we use an integrality, right? So we're using integrality to claim that both of these quotients must in fact be integers, and so they're equal to some delta. And actually, this equality that delta is precisely v14 minus w14, requires proof, and this is what we mean by a calibration calculation, because of course these two things are not by default the same. The fact that they're equal is a non-trivial consequence. Okay, but by introducing this delta, we can think of this as a pair of Pfaffian equations, just by cross-multiplying with delta from both of these terms. Okay, so the calibration calculation deserves to be seen once um, because they're all very similar. Okay, so the idea is that, well, again, we use the fact that this system, if it's not full rank, then it has to be rank 2, and it can't be the zero matrix neither because, well, these terms can't be zero, right? Because they're also parts of the parameterizing sequence, so the rank has to be exactly 2. And doing so allows us to explicitly write S3 and S6 in terms of S9 and S12 and the other terms and the coefficients of the matrix. So we start with that, and by digging deeper, we can isolate even more variables in terms of the rest. Okay, so that allows us to feed everything into just the transfer variable. We know that the transfer variables must satisfy this equality, so we calibrate it. So this giant mess, whatever it is, has to be equal 1. And we used a substitution to compute this. Well, it turns out that it just staring at these two terms staring at these two terms, this is exactly delta times the first one because you have this one extra delta in the denominator. Okay? So that means that, well, this is, so delta, and we already know this is 1, so delta has to be equal to this difference. Okay, so this is not really easy. I don't know how would I've done this by hand. I mean, I could have if I knew what I was looking for, but there's probably like 1,000 ways to make a tiny mistake so that you'll miss that these two terms are actually equal if you do it by hand. But yes, so this is sort of a miracle. Okay, so this is what I call a calibration calculation. So this allows you to to say that these quotients coming from the Pfaffian equations is precisely given by the difference of transfer variables. Okay, so we also obtain this, which,
Sorry, can I have a question?
yes.
In the previous slide, did you have a typo? Because you have the same denominator. There is no extra delta or maybe I'm missing something.
Oh, yeah, yeah. So yes, I think
Okay.
this is not supposed to have a delta.
Yeah, okay, thank you.
Yeah. Okay, so finally, we consider a non-trivial quintuple Buchi pairs. Okay, so it must then come, if it exists, it has to come with a potentially positive parameterizing sequence S. So this parameterizing sequence has 32 terms, making it fairly unwieldy to work with. So I'll just display it. So it's this. So when I first came up with this, I was working from home in Ontario, and my wife was working behind me, and I told her, hey, take a look at this. And then I don't remember exactly what she said, but it was something like, did you just have a stroke? Right? What is this? Right? It's really messy. So yes, so trying to work with this is unwieldy. And when I first got here, I was like, okay, well, what am I going to do with this? And there was nowhere to go but forward. Okay, you just keep going and hope for the best. And luckily for me, it did get somewhere. Okay, so we can further assume something about the transfer variable by swapping xj and yj, which I've said a few times before. So we can always assume that this holds. But other than that, we can only determine things up to sign, but we can't figure out the exact value. So we just have to introduce these things called structural constants. So that means that if you jump twice, you have the beta j's. If you jump 3 times, you have the delta j's. And because you're dealing with a quintuple, the first and last one has a difference of 4. So you call that gamma. And gamma, this is the first time you don't have unique factorization because 4 is not a prime. So you have to deal with uh, more possibilities. Like there could be 1, 4, 2, 2, or 4, 1. Okay. But that doesn't end up being super, super important. But that's just an observation that my point is if this doesn't work for n equals 5, it gets much harder for n equals 6. Okay, so it's lucky that 5 is enough. So as a direct consequence of an n-tuple Buchi pairs in our choice of labeling, that's just kind of bookkeeping, right? All the beta j's have to be between 1 and 2, and delta j's have to be 1 and 3, but gamma could be 1, 2, or 4. Okay, so now from a quintuple of Buchi pairs, you can't just delete the first and last row like we did for quadruples. It turns out you have to delete one row at a time. Okay, so if you delete the first and last row, then you just get like a quadruple of Buchi pairs, like the way we defined it. But if you delete one of the middle rows, then you're going to screw up the structure, or it's not, you're going to screw up the consecutive differences. Okay, but nevertheless, this is a necessary step. You just have to figure out what to do with that. Okay, so that's what I said about B1 and B5 if you delete the last and the first row. So B2, B3, B4 are not quite quadruples of Buchi pairs because the differences between consecutive rows are not always 1. But by adjusting for this difference, one still gets analogous non-triviality conditions induced by a Pfaffian equation. So the structural shape of the matrix, that is a skew-symmetric matrix, doesn't change. Okay, which is, I don't know how miraculous that is, whether that's meant to be, but that does happen. So at the end, by deleting each row, you're going to get 5 pairs of Pfaffian equations for the parameterized sequence S. And I call these the structural equations. So they're given by, okay, so there's a massive system of equations. So there should be 10 of them in total, 5 pairs. Okay. And I grouped the terms together in a specific way. So if you, and this is why I think the way the choice of labeling is really important because this pattern is not that easy to spot. If you look at these terms, right, the indices always add up to 31, the way I grouped it. Okay, so that allows you to make a change of variables and just write this as like T2 or something. Okay, and that's exactly what we're going to do. So staring at this, I think it's magnificent. The fact that they actually group up like that, I don't know why it happens that way. So one notes that it can actually be expressed as a system of bilinear equations in the variables T1, T2, and the TJs are defined as Sj times S31 minus J, right? Using the fact that they always add up to 31. Okay, so and uh, and if you look at it, these are all bilinear, and they're sorted into 2 sets. So a set of 5 terms and a set of 15 terms. Okay, so fixing this S heart, which is the 5 set, and viewing this big system as a linear system in the S spade, which is the 10 set, we're going to get a 10 by 10 system, linear system given by this matrix. So it's a pretty big matrix, but it's pretty sparse. Okay. So it's not hopeless that something actually happens. But it turns out that there's not much, you don't get a lot by studying this matrix, but you still get something. So if S is to be positive, then S spade must be non-zero. Every term in S spade must be non-zero. And therefore M must be singular. So unfortunately, M is generically singular. So the rank, just symbolically, is 9. Well, I use Sage to compute a bunch of 9 by 9 subdeterminants and see what needs to happen in order for it to be for them to vanish. So it turns out that some of the 9 by 9 determinants are just zeroed also generically. So the unique null vector you get by taking the generic case is not usable because it had zeros in it. Okay, so you actually need the rank to drop below 9. Uh, so it turns out that the only condition you need for the rank to drop below 9 is if the structural constants beta 1 is equal to beta 3. Okay, so once this happens, the rank actually drops to 7. So you can't actually make the matrix rank 8 uh, without without failing right away by making some of the TIs 0. So, okay, that wasn't too exciting. But if we flip the bilinear system and we say hold S spade constant and consider the system as a linear system and S hard, then we're going to get a 10 by 5 system given by this matrix. Okay. So the same thing happens. You need the system to have low rank. You can't have this be full rank. And luckily, this time, this is generically rank 5. So insisting that it's rank at most 4 is non-trivial. So if we are to have a non-trivial parametric sequence, this matrix M has to be singular. And that means you have to make sure all 10 choose 5 equals 252, 5 by 5 subdeterminants all have to vanish. Okay, so that's a lot of determinants to take, and calculating a determinant by hand is terrible. I tend to not make my students do that in a linear algebra class, so I use the computer. So we're going to label these subdeterminants by di1 up to I5, and we adopt the convention that the rows are labeled from 0 to 9 instead of 1 to 10. So the miraculous part of the proof is that you don't actually need a lot of determinants to tell you that things aren't going to work out. I think I only need, at the end, the proof only requires 10 of these subdeterminants. But it took a long time to find them, right? I calculated way more than that, but at the end, you only need about 10. Okay, so the first lemma is that this is just proof by basically computer algebra, right? You have these particular indices and these particular consequences. So they factor very nicely. Okay, so you have these bilinear terms, and you have something that, and the rest of it is just obviously non-zero if you assume non-triviality, right? Like the T14 can't be 0 and the structure constants can't be 0. So from here, we derive that, well, exactly one of these terms have to vanish. Okay, so you just have to study the very last term actually. So that's when they're both 0, right? So if you want this to be 0, then one of them has to be 0, and they cannot both be 0 without violating non-triviality because their sum is something that basically can't be 0 without either T12 or T13 being 0. Okay, so we can actually insist that beta 1 equals beta 3 because we want this to be rank less than 9. So if we start with a non-trivial quintuple Buchi pairs, and given the structural constants, we say it's type 1 if this happens, if this term vanishes, and type 2 if this term vanishes. And then you just have to show that, okay, neither type 1 nor type 2 contain any non-trivial members. Okay, so remember I emphasized positivity. So it turns out that this is relevant to the proof. Um, so I'm just going to give the proof for type 1, which gives the flavor of what happens, and type 2 is basically the same, but I mean, it's a little ad hoc, right? But similar flavor. So by the assumption that this is not 0, we can show that, well, this term appears in other terms here, right? I think, for example, this line and this line. So we conclude that the other term in that line has to vanish, and you get these equations as a consequence. So you prove a lemma. Again, integrality plays a role so that you can actually say that this has to be 1 just because of the visibility conditions. Um, so you just every step that you are able to prove something, you feed that back into the linear system and see what you can get. And if you feed this information back into D02457, you get this equation. And this is where positivity matters, right? Because this term can't be 0 anymore, right? Because of the positive sign. So that forces this term to be 0. Okay? So you immediately conclude that this term has to be 0. And well, if you compute some other stuff, you look at this particular subdeterminant, again, you have positivity, which means that this term has to vanish. Okay, so you have this equality. And if you combine them, well, you have this. So you substitute away T7 and T14. And once you succeed here, you actually done it. Okay, if all these conditions are satisfied, then M just drops to rank 4. So are no other obstructions to there are no other 5 by 5 subdeterminants that remains non-zero after you make these substitutions. So okay, well you might be in trouble because now you actually do have non-trivial solutions. But again, if the rank is just one less than the full rank, there's a unique null vector. There's no freedom, right? It's all the non-trivial solutions are scalar multiples of that one vector. But unfortunately, that one vector that you get has a zero component. So again, there are some once with all these conditions involved, there are some 4 by 4 subdeterminants that just vanish generically. So there are holes in the null vector. So the only way to try to get non-trivial solutions is if the rank drops even further. Okay, so we can study just one 4 by 4 submatrix. Okay, and we just look at all the 4 by 4 subdeterminants of this one matrix. And just from here, we get something that does vanish generically, right? So if you delete the 0th column, you get something that vanishes generically. And say if you delete the 3rd column, you get something that looks like this. And well, because we want the rank to drop even further, this actually has to vanish, which means that this term or this term has to be 0. And if you try out a bunch of other subdeterminants, you get some other thing that also has to vanish. So you get this has to vanish. And well, if you set this equal to 0, you get this equality. And these are incompatible linear equations in the sense that the only solution will be the 0 vector. And that forces some of the TIs to be 0. And that means that you actually don't have a non-trivial quintuple. Okay, so that is essentially the argument, and I'm basically out of time with 1 minute left. So thanks. Uh, I do have a bonus slide for people who care about the algebraic geometry of the problem, which is to say that this is the system that Wojta considered, right? So this system defines a projective surface. The way I labeled it here, I think it actually is Pn. So geometrically, for x3, just have the first line, that's just a quadratic surface. X4 just turns out to be a Delpezzo surface, and that explains why they actually have lots of solutions. And for n greater than or equal to 7, I think you have or for n equal to greater than 8, you have a surface of general type. So the n equals 5Ks is actually a K3 surface.